Welcome. This is the causal inference chapter. So what is a causal inference? So we're trying to infer, is it something cause some other things? So inferring the effect of something to something. So effect of the treatment or effect of the policy. Yeah, we already seen the similar things in the regression model. So we wanna really find out the effect of A on B. Okay, is it A cause B or not? And if it's causing, then what would be the magnitude of the effect? So answer to the question of the did A indeed cause B? So we want to find out this causal relationship. So using the data and statistics, maybe we can infer about this causal relationship. So motivation is from the Simpson's paradox. You may heard of Simpson's paradox from some statistics course. But in 1973, on the UC Berkeley Graduate School admission, actually there was kind of the big issue because the somebody raised the problem. Actually, UC Berkeley, the graduate school, discriminate women. So they show the data. So actually, the men, there was more than 8,000 applicants, and 44% of them got admitted. And then women, there's more than 4,000 applicants, but only 35% got admitted. So they raised the problem. As you can see, obviously the woman got the lower admission rate. So now the question is is it the being woman cause a low acceptance rate? The difference is statistically significant. It seems like, but can we say is actually the woman caused the low acceptance rate, which means there was a discrimination? Okay, this is the detailed data. We take a look at the 6 largest department and in UC Berkeley, and then A, B, C, D, E, F department. And if you look at the department level data, department A, men's admission rate was 62, but women's admission rate is 82. Women have a way higher the admission rate. Department B, men got a 63, women got 68, so not a lot, but still women got a higher. Department C, men got higher admission rate. Women's got a little lower, but not a lot different. Department D is pretty similar, but women got a little higher. Department E, men got higher, but not a lot different. And then F department, actually women got slightly higher admission rate. So if you just take a look at the department level data, it doesn't look like a woman got discriminated, right? But when we aggregate, the percentage will be 45 versus 30%. This is an even bigger difference when we see the whole university level admission difference. Why these things happen? Actually, A and B, I guess this is more like a engineering school, engineering department. I don't know what is a C and F, C, D, E, and F. Usually, this department is a kind of the English or like literature or the social science department. Why the engineering department accept way more applicant is actually engineering department can get a lot of fund from the company. So they have a lot of money to hire. So that's why the engineering school usually accepts the more graduate student. And as you can see, how many applicants we have, man applicant for the department A and B, it's a lot of them are men, but few of them are women. Actually, if you look at the department B, out of 585 applicants, 560 of them are men. Only 25 women apply for the department B. So if you take a look at the tendency here, roughly we can tell men apply for the more like a generous department. Most of men apply for the department A and B, which are the department they admit a lot of the applicant. And the women tend to apply for the department C, D, E, F. Those department doesn't accept a lot of the applicant. That's why even though department by department, I don't see any discrimination. But when we aggregate, because a lot of women apply for the hard department to get in, but a lot of men apply for the easy department to get in. So men got a higher admission rate as a aggregate. Women got a lower admission rate. But when we look at the department by department, actually this one is not true. So this is the same thing can happen when we look at the group by group. Actually, relationship is the negative relationship, negative correlation. Right? Group by group, right? This is a different group, different group, different group, and then you can see in all of the group it has a negative relationship. But when we aggregate this group, what you can see, the relationship is positive, right? So that's what we call the Simpson's paradox. Simpson's paradox. If you look at the group by group, actually relationship is the opposite direction. Negative relationship, whatever is x and y. X and y has a negative correlation. But when we aggregate the data, this looks like a positive correlation. So it's the same thing here. When we look at the department by department, actually, maybe University of Berkeley was give a favor to the. I think this is a woman got higher admission rate if you would look at the department by department. Not all departments doing that, but however, when we aggregate all the applicants, actually men got higher admission rate. Yeah, of course that just happened, end up with like a happening once the UC Berkeley opened the department level data. But this can happen. So we cannot just easily say women got discriminated because the woman's admission rate is way lower than the men's. So correlation is not causation. So causation means it's something cause some other things, but correlation is whenever something goes up, the other one also has a tendency to go up. Then we can tell there's a correlation. But A has a high correlation with B. That does not mean A cause B. So think about it. If you just measured, you are selling the umbrella, so you measure the umbrella sales, and also you somehow measure the moisture in the soil in the backyard. So you have a backyard, and then you have like a soil, and then you just measure what is the moisture of the soil in the backyard. And if you plotting your umbrella cell and moisture in the soil in the backyard, they will have a high correlation. So maybe moisture in the soil in the backyard cause the umbrella sales. And if you want to sell more umbrella, maybe you have to pour the water on the soil in the backyard. Is it right reasoning? Of course, no. Yeah, of course not. It doesn't matter how much you pour the water on the soil in the backyard, your umbrella cells will not change, right? This is the now. This example is just obviously I know this is not the right, but when we have a lot of complicated situation, we cannot tell this is wrong or not. So we assume the moisture in the soil caused the umbrella cell, but obviously this is not. Well, what happened? In fact, what happened is that when there's a rain, right? So rainy day, umbrella cells goes up, and also since there's rain, moisture in the soil in the backyard goes up. Every time there's rain, both of them happen together. That's why we have a when we have a high moisture and then high umbrella cell, low moisture in the soil, we have a low umbrella cells, right? So it seems like it's happening together, but actually none of this is causing the other. But we are easily fooled, and you can see that these two graphs, the red chart and the black chart, is pretty match up to pretty well, right? So if you take a look at it, what is this one? Is actually the black one is the babies named coral, right? The babies of all sexes born in the U.S. named coral. So you just count how many babies at that year, specific year, there's a lot of babies were born, and then how many of them named coral. Yeah, that's the black chart, and then red chart is the biological technician in Missouri. So how many biological technician in Missouri? Missouri is the state of one of the state in U.S., right? So biological technician, number of biological technician in Missouri has a same tendency. So which means if you name the baby, a lot of people named their baby Coral, actually we will have a high number of biological technician in Missouri. That doesn't make sense, but actually they have a high correlation. Whenever they goes up, the other one also goes up, and one goes down, and the other one also goes down. That does not mean one thing causes the other things. And this is kind of funny. Our brain is just, I don't know, by the genetically trained, when you see something and then you trying to connect, trying to figure it out what happened. So as you can see, the name of this picture is never underestimate the power of the dog. So it seems like a dog crashed the steel door and then walk in. Yeah, obviously it's not true, but yeah, when we see this kind of scene, and we might imagine the dog break the doors. So we have that kind of tendency. So whenever this is kind of the obviously wrong conclusion, but when the situation is you don't know exactly what caused which one, we are easily fooled.